Hello everyone and welcome back to the Inorganic Tutors Institute. So we begin lecture 2 today, and today we are going to discuss unions, intersections, independence and their applications. These stuff involve a lot of practical work, so today we are going to solve countless problems and make sure we really understand what each of these concepts tries to bring about, such that when we are given any question, we will be able to attempt them in the right way. And mind you, this concept is very key in probability, so it's essential that you do well to understand each part of it. Pause the video if you don't get it, reverse, and try your hands on the questions that you might see along the line. So without wasting much time, we will kickstart and see what today's lecture has for us. Once again, this is brought to you by the Inorganic Tutors Institute, and my name is Nasiruddin Gati. Okay, so right away, let's talk about what the union of a set is. So we have here that the union of two events, A and B, written as A, U, B. So that's the symbol for the union, a U sign, as you know from your senior high and your basic levels. So written as A union B contains all outcome in either A or B or both. And this is the core of what union actually talks about. Either A or B or both. Either in A or in B or both of them. That is what union talks about. Okay, so if you have this and you have A here and B here, the union talks about what is here, what is here, or what is between the two. So ideally, the union covers everything in either A or B or both of them. So if you are present in A, you are considered. If you are in B, you are considered. If you are in A and B, you are also considered. Take note of this, because this is what you need whenever you see A union B. Okay, good. So this is the formula you will use when asked questions under union of sets or union of events, and it is very, very important. Never forget this formula in your life once you are a probability or a statistics student. Never forget that the probability of A union B equals PA plus PB. One mistake most students make is that they treat probability of A union B as this, ignoring the third part. It's very, very dangerous. Never try that anywhere, okay? And if you've learned this anywhere, don't use it anymore. Well, in some situations, this formula is right, but it's just for some situations. And in those situations, you can still go by the main formula. Just that this part will be 0. So if you don't want any trouble, just keep the main formula in mind all the time. When you are working and it happens that the last part, the intersection part, is 0, fine. But in cases where you have to use the whole thing and you use this short version, then that becomes a problem. I'm giving you the advice again. Whenever you see PA union B, treat it as PA plus PB minus their intersection. Good. So that is how to define them. So make sure you have this written down in your notes. And we will solve countless problems where we will employ this. So buckle up and get ready for all those. Now we move on to the intersection of two events. So the intersection of two events A and B, written as A, that symbol, and B, so A intersection B, contains all outcomes common to both A and B. Common, okay, common to both A and B. Okay, common to both A and B. So that is what we mean by the intersection of two events. Okay. Ideally, the intersection doesn't have a standalone formula. Okay, it relies on the formula that we saw earlier about the union of sets. Okay, so you just make the intersection the subject and you get your new formula. So this part is the intersection. Okay, this part, that's the intersection. So if you want to, sorry, this is N, not U. So if you want to get a formula for the intersection, you make this the subject by bringing this to this side and bringing this to this side. Okay, so this is what I mean. P, A, and B, intersection B, equals a PA plus PB plus the union. Sorry, not plus, because we are moving the union to this side, it becomes negative. Okay, so the two formulas look very identical. So if you want the intersection, it's A plus B minus the union. If you want the union, it's the A plus the B minus the intersection. Okay, that is how it works here. Okay, there is no other formula for intersection unless there is a specific situation. Okay, unless there is a specific situation, and we will see those situations when we move along. When there is independence, when they are mutually exclusive and all those stuff, you will get to see them. But those are for certain conditions or situations, not the general formula. So this is actually the general formula for the intersection that you should know. Okay, good. Let's move on. So we have mutually exclusive events. Mutually exclusive events. Yes, we saw this when we were treating, we were having our first lecture. We saw what we mean by mutually exclusive. And I mentioned to you that mutually exclusive events events, they do not happen at the same time, or they cannot occur together. When we were talking about events and we listed some outcomes, and I told you that for it to be an experiment, the outcomes should be mutually exclusive. Okay, so when one occurs, two does not occur. When you roll the die and you get 3, 4 cannot occur. So two numbers cannot happen at the same time. You can't roll a single die and get 3 and get 4. Once you get 3, 4 cannot happen. That's what we mean by mutually exclusive. They cannot occur at the same time. So if events A and B cannot occur at the same time, then their intersection is 0. If it is given in a question that A and B are mutually exclusive, then it means that their intersection is 0. And this is a way to visualize it. Let's say we roll a die and A is the outcome of even numbers. So we have 2, 4, 6. B is the event of odd numbers. 1, 3, 5. Okay, now what is the intersection? Nothing at all. Okay, there's nothing in the intersection. And remember, to determine the probability of an event, it is the number of outcomes over the sample space. And here is the case, we are getting an empty set. We saw A intersection B to be empty. In that case, the number of elements in A intersection B, the number of elements here is 0. So we don't even care what the sample space is giving. That's why we see that it's 0. So if the two of them cannot occur at the same time, that means that their intersection is 0. And if the intersection is 0, then the probability is also 0, because we divide the number of outcomes inside by the sample space. So if there are no outcomes, if they can't occur at the same time, then we have the probability also to be 0. Okay, good. So the two things you have to note from here: if two events are mutually exclusive, or if they are stated to be mutually exclusive, it means that they don't have an intersection. The intersection is empty. And for that matter, their probability is also 0, because the number of outcomes that they have is 0. They have no outcome. So whatever number you divide by 0, it will be 0. So take note, mutually exclusive. Good. Let's proceed to the next items, which is independence, which is very, very important in probability and statistics. Very, very important. Independence. Okay, so we say two events are independent. It doesn't mean they can occur at the same time, or it doesn't mean they cannot occur at the same time. Maybe they cannot, maybe they can. That is not the matter. The matter is that A occurring does not affect B. Okay? And B occurring does not also affect A. Take note. Independence. The occurrence of the first event does not affect the occurrence of the second event. Okay, and the occurrence of the second event does not also affect the first event. So what practical example can I give for this? Okay, let's say it's A is an event that it rains. Okay, and let's say B is the event that, okay, let's say you pass an exam. Good. Let's use these two examples. A is the event that it rains, and B is the event that you pass an exam. Do you think they have any connection? It's looking like they want to have a connection. So maybe let me use a better example. But why will raining cause you to pass or fail an exam? Okay, but well, let me give another practical example. Okay, so let's say A is the event that team A wins a match, a football match, or let's say a match. And let's B be the event that a lady delivers sorry about the writing, a boy. Good. So event A is that team A wins a match, and B is that a lady delivers a boy, a baby boy. So what we can see from these two examples is that team A winning a match has nothing to do with B. You winning a match wouldn't make a lady deliver a baby boy. So you are telling me because you won, that's why she had a baby boy. If they hadn't won the match, then she would have delivered a lady or a girl. That's not the case. It makes sense. It makes no sense to anyone. So we say this event A and B, they are independent. They don't depend on each other. What is happening in A has no connection to what is happening in B. And what is happening in B, a lady delivering a boy wouldn't make team A win their match. So you just go somewhere and say, oh, team A won their match because this lady delivered a boy. Makes no sense. It has no connection. So it could be that team A will win and the lady will deliver a boy. Fine. It's possible. It may be that team A will win, but B will not. The lady wouldn't deliver a boy. What argument am I trying to bring? I'm trying to tell you that independence doesn't have anything to do with occurring. If they are independent, it doesn't mean they cannot occur together or they can occur together. It doesn't really matter. If they are independent, they can happen together, or it might be that they might not happen together. That's not the concern. The concern is that whether they happen or they don't happen, one doesn't cause the other, or one doesn't have anything to do with the other, or one does not depend on the other, hence the name independent. Okay. So that is actually what independence mean in probability, meaning the two doesn't have any connection between them. So there's also a very important thing you should note. When two events are independent, the intersection can be obtained as PA times PB. So if you see in the question that A and B are independent and you're asked to find the intersection, you can multiply the probability of A by the probability of B. But when you're not told that A and B are independent, and never assume it, never assume that, oh, they are independent, so let me just multiply to get the intersection. No. You can only apply independence when you are told that the two events are independent. If not, never find the intersection using this formula, but find the intersection using the formula that we saw: A plus B minus the union. Okay, please take this from me. All right, so let me make this last deduction from the two slides we've just seen. If they are mutually exclusive, so let me write mutually exclusive, then their intersection is 0. If they are independent, then their intersection is the product of the individual events. Keep these two things. Good. But for mutually exclusive events, you are not always told. For that one, at times you have to deduce yourself. Because if a student is taking a test which is true or false, remember that the answer can't be true and false, meaning true and false are mutually exclusive. They can't happen at the same time. The answer can't be true and at the same time be false for the purpose of this course. So for mutually exclusive, at times you have to deduce them. Looking at the events, you will know that there's no way two of them can happen at the same time. But for independence, wait to be told. Okay, good. Let's move on. Now we start our series of examples. So from now to the end of the lecture, we are just going to solve examples, a lot of them. Don't get bored when I don't finish on time, or when you expect me to finish and there are still more and more examples coming. Okay, as usual, you can pause if you are tired and come back another time. The channel is here for you. It's always there. Okay, so let's kickstart with our first example. So we use this preamble to answer the next set of questions unless there is another preamble given along the line. So it says that we are dealing with two selections with replacements. Okay, so we have the numbers from 1 to 10 and we are selecting 2 with replacement. So this is also a very important term you should note. With replacement, meaning after selecting, put it back. Or after selecting, the one that you selected is still in the sample space. So if it's from 1 to 10 and you select 9, the second person coming to select also has the possibility of choosing 9, or we replace 9 back. Okay, you will better understand when we kickstart with our examples. So 2 numbers are selected with replacement. Calculate the probability that both are even. Calculate the probability that both are even. So now we no more deal with situations when we will list all the events. No, it's not always the case that you have to list all the events, but you need to know the sample space. For the sample space, you need to know it. So in this question, our sample space is 1, 2, 3, up to 10. Okay, that's the sample space. And we are making 2 selections. Okay, so this is the sample space for just one selection. Okay, so this is actually not the sample space for our question, because our sample space, our selection is done twice. So ideally, the sample space should be the first selection has 10 outcomes times the second selection that we will do also has 10 outcomes. Remember, there are 10 numbers, so you can choose any of the 10. So the first selection has 10, second selection has 10, so a total of 100 outcomes. We saw this in our previous lecture. If not watched it, do well to make yourself comfortable with the concepts there before you come here. So the number of sample space is 100 because the first one has 10 outcomes, the second selection also has 10 outcomes. So let's put this down. Number of sample space equals 100. Good. Now, we want the probability that both numbers are even. let's do this. Because the sample space is very, very huge, 100. If we are to list the events one after the other, the outcomes that the two of them are even, we might spend some time, because we will have 2, 2, 2, 4, 2, 6, a lot of numbers. So one smart way to do it, or the recommended way to do it, is to first find the probability that the first selection is even. The probability that the first one is even. And the even numbers, we have 2, 4, 6, 8, 10, 5 of them. So the probability of getting the first one to be even is 5/10. And you go ahead and find the probability that the second one is even, which is also 5/10, because it's the same as what the first guy did. So the probability of getting an even number in the first selection is 5/10, and the probability of getting even in the second selection is 5/10. So both being even means that the first one is even, and take notes for probability, and means intersection. Okay, this first one is even, and second one is also even. First one is even, and second one is even. That is intersection. To get that, we multiply this by this. Okay, so actually, we weren't given that the two events are independent, as I warned you about. But looking at this, okay, well, maybe I should correct that. Not always should you expect the situation to be given as independent. Just that for matters relating to selection, okay, when you are doing two selections, mostly selecting the first one doesn't have to do anything to do with the second one. And that is only true when we have with replacements. So in other words, with replacements means that the two selections are independent. So, well, we were told, but it wasn't direct. So the with replacement here is telling us that the two selections are done independently. Okay, so now we multiply the first one to probability that both even is that the first one is even and the second one is even. That gives us 25/100. So there's a probability that both are even. Okay, good. Now let's move on to the next question using the same preamble. Probability that at least one is prime. At least one is prime. And let me also teach you this. At least is a big fan of complements. We saw complements in our previous lecture, where the probability of E equals 1 minus not E. So you put a bar or a 1 or a C. So the probability of E equals 1 minus not E. That's what we mean by complements. And at least one is a big fan of complements. Okay, very, very big fan. That's what I mean. At least one means that either you get 1 or 2 or 3 or 4 or whatever. It's just saying that you should get 1 or more 1 or more. So there's no up, you can get like 17, but you should get at least 1. And an easy way to do that is that the probability that of at least 1 is equal to the 1 minus probability of none. Take notes. Probability of at least 1 is equal to 1 minus none. Okay, always. So whenever you see probability of at least 1, you can always apply this 1 minus none. Okay, good. So to solve this problem, let's find a probability that we get no prime. And remember, we are choosing 2. So the probability of getting no prime in the first one. So prime numbers. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the numbers that are not prime numbers, we have 1. Mind you, 1 is not a prime number. 4 is not prime. 6 is not prime. 8 not prime. 9 not prime. 10 not prime. So in total, we have 1, 2, 3, 4, 5, 6. So 6 numbers are not prime numbers. So 6 of the numbers are not prime numbers. Okay. So I want to find a probability that in the 2 selection, none of them is a prime number. None of them is a prime number. So the first one shouldn't be a prime number, and the second one shouldn't also be a prime number. So the probability that the first one is not a prime number is 6/10, because we have 10 values and 6 of them are not prime. So the probability of not getting prime in the first one is 6/10. And the probability of not getting prime in the second one is also 6/10. Okay, so the probability of no prime is the first one is not prime and the second one is not prime. This is the probability that the first one is not prime. This is the probability that the second one is not prime. As we saw, we have 6 numbers that are not prime out of 10. So the probability of not getting prime is 6/10. For the second one, the probability of not getting prime is 6/10. So for probability of not getting prime in the 2 of them is 6/10. That is not getting prime in the first one. And here is times. And not getting prime in the second one. Okay, giving us 36 out of 100. Remember, this is the probability of not prime, or none of them is prime. So the probability of at least 1, the one that we are finding, this is at least, is equal to what? 1 minus none, as I stated earlier, which is 1 minus the none, which is 36/100. So the probability of at least 1 is finally 64/100. Very simple. So we are selecting and want the probability that at least like among the two numbers that we select, at least one of them should be prime. And I told you that when you see at least one, it's the same as 1 minus none of them is a prime number. So we went ahead to find the probability of none. Probability of none means that the first one is not prime and the second one is not prime. The probability that the first one is not prime is 6/10, and meaning we are multiplying. The second one is not prime, it's also 6/10. So we get the probability of none to be 36/10. But that's not what we were asked to find. So we find at least one as 1 minus the none, and we end up getting 64/100. Okay, good. So let's proceed to the next item. Probability that either number is a perfect square. We also have a new probability term here, either. So when you see either, it relates to union. So know this probability language, okay? Yes, we saw at least one. It was related to complements. And we are seeing either, which is related to union. We also saw both, which was related to intersection. So we'll be picking this stuff, okay? Either union, both intersection, at least one complement. Okay, good. So let's go ahead and find this probability. So either is a perfect square. Okay, either is a perfect square. And we have that probability of A union B is A plus B minus the intersection. Okay, so let's go and find PA, let's find PB, and let's find the intersection. Okay, so probability of A here, I mean that the first one is a perfect square. So probability that the first one is a perfect square. How many perfect squares do we have? We have 1, 4, and 9. In that case, the probability that the first one is a perfect square is 3/10. Now, the probability that the second selection is also a perfect square. There are still 10 numbers there, because whatever we pick, we put it back for the second selection. So the first one and the second one are almost the same. So the second one too, the probability that we get it is 3/10, because there are still 3 perfect squares with a total of 10. Okay, now the probability of first one being perfect and second one being perfect. Remember, the activity is without replacement, so it's with replacements. So we have 3/10. So the first one is a perfect square and the second one is a perfect square. So this is how the intersection looks like. The first one is a perfect square and the second one is also a perfect square. Okay, good. So take note of these probabilities. This gives us 9/100. So we are working with PA, PB in the intersection. Okay. So finally, probability of either number is a perfect square is probability of A plus B minus the intersection. Let me do that on my calculator and see what I will obtain. 3/10 plus 3/10 minus 9/100. So when you do it well, you should get 51/100. Okay, so this is the correct answer to the question. Let's move on to the next question. Probability that none is a multiple of 3. None is a multiple of 3. So it means that the first one is not 3, and the first one is not a multiple of 3, and the second one is not a multiple of 3. So the first one is not a multiple of 3, and the second one is also not a multiple of 3. See how I'm stressing on the and changing to n intersection. First one is not, and second one is not. Okay, so let's find the probability of not getting a multiple of 3. So let's count the numbers there that are not multiples of 3. So 1, 2, 4, 5, 7, and 10. 1, 2, 3, 4, 5, 6. So there are 6 numbers that are not. No, sorry, there's 8. There's 8. There's 8. So it's actually 7 numbers that are not multiples of 3. So the probability of not getting a multiple of 3 is 7 over 10. So probability that none is a multiple of 3 means that the first one is not a multiple of 3, and the second one is not a multiple of 3. I already told you and stands for multiplication and or stands for addition. You will see situations where we will say or instead of and you should master this through solving multiple questions and watching Inorganic Tutors Institute all the time. Sure. So we have this, and that gives us 49 over 100. Okay, that gives us 49 out of 100. The first one is not a multiple of 3, and the second one is not a multiple of 3. That means that none is a multiple of 3. And that satisfies our question. Okay, let's move on to the next question. The first number is even, and so this one you are lucky that the end has been bolded for you. So the first one is an even number, and the second one is a perfect square. The first one is an even number, and the second one is a perfect square. So let's first know what's the probability of getting an even number on the first one is. So there are 10 numbers and 5 of them are even numbers. So this is the probability that the first one is even. Now let's find the probability that the second one is a perfect square. We have 3 perfect squares, so the probability that the second one is a perfect square is 3 over 10. Okay, now to do the multiplication, it says the first one is an even number and the second one is a perfect square. Okay, which gives us 15 over 100. If you want to break it down, you can get a 3 over 20. But the most important thing I want you to note is that it says the first one is even. This is it. And this is the end. Second one is a perfect square. This is it. As simple as that. Okay, good. Question that we have, it says calculate the probability that the first number is odd or second number is prime. or second number is prime. So this basically translates into a union. The first number is odd or the second number is prime. Okay, so we have a union. Okay, so we have P odd plus P prime minus the intersection. This is what a union translates to. Okay, ideally, in situations where they cannot intersect, union just simplifies to addition. That's why I mentioned that or implies addition. But in this case, there can be an intersection. It could be that the first number is odd. Maybe that number is 3. Remember that 3 can also be a prime. You get it? So there are situations where they will be overlapping. It can happen here and happen here too. So we have to deduct that one. To illustrate it better for you, which might not be so relevant, so let me pause it there. So we have or, and that is translating to a union. Okay, so whenever you see anything like or, have union in mind. If it happens that the two events that you are considering, they can't happen together, and it just reduces to a simple sum, first event plus second event. But when there's a chance they can intersect, bring that. Okay, good. So let's tackle this. So the or translates to O union P. It is PO plus PP minus their intersection. So what is PO? The probability of odd, we all know, is 5/10. And the probability of prime, the prime numbers, we have 2, 3, 5, and 7. So 4 of them. So we have 4 out of 10. So once you have this, you are almost done. Okay. So the final probability is 5/10 for odd plus 4/10, because the activity, the first one doesn't depend on the second one, minus 5/10 times 4/10 times 4/10. When you do this correctly, you end up with 7 out of 10. And that's the correct answer. Okay, so the or here implied union. Okay, good. So learn this language. I think that's all the questions for the replacement. So let's do a small recap. So I mentioned that at least goes with complement, which is 1 minus none. So that and tells us to multiply. So that or gives us a union or tells us to sum. But when summing, you should also be mindful that there could be situations where they will intersect. When they intersect, you have to deduct that. Okay, so keep this important language, at least, and or. Okay, good. So the end can also be, say, intersection. Yes, this happening and this happening, we multiply. Okay, good. So let's move on to the second set of questions. So we have 2 selections without replacements. So things have changed now. We are not replacing. So when you pick, it affects so let me take it again, inorganic. So this is the second set where we have 2 selections without replacements. So this one, we don't put it back. So what I have affects what you choose. If I select 3, you can't select 3. And this is where it moves from so simple to a bit technical, where you have to be careful. So we have the same numbers 1 to 10, but once you pick the first one, you don't replace for the second selection. So we will be mindful here. So probability that both are even numbers, just as we saw. So probability that the first one is an even number and the second one is an even number. 5/9, because previously I wrote 5/10. Remember, in this situation, we don't put it back. So if you pick one even number here, we are left with 4 even numbers, and we are left with a total of 9. Remember, this event says that the first one is even. So you've taken one even number out. Okay, so we have 4 even numbers left, and the total number of balls that we have are 9, because the first one picked 1. So we still don't have 10 items, we have only 9. And the first one picked an even number, so we have 4. That's what makes without replacement different. So when you do the first event, it affects the sample size of the second. So the first one says that we have 10, we are choosing one even number. So if I want to choose another even number, there are 4 left and a total of 9 items. Okay, so this nicely gives us 20/90, or in other words, 2 out of 9. Okay, good. Let's proceed. Probability that at least one number is prime, which is the probability that of 1 minus none. So at least it's a probability of 1 minus none. Always, whether with replacement, with whatever, is always 1 minus none. So let's find the probability of none. It means that the first one is not prime and the second one is not prime. So what is the probability that the first one is not prime? Remember, we have 4 prime numbers. That is 2, 3, 5, and 7. So not prime means 6/10. So this is the first one. And we want a case where the second one too wouldn't be prime. But remember, we've already taken out one number which is not prime. So the numbers that are not prime reduces to 5. And because we've taken one item out, the numbers are a total of 9. So it's like the without replacement, we reduce them by 1, 1, 1. Especially the denominator. For the numerator, it's not always the case. But the denominator, mostly we reduce the sample size, because the first event picks out 1. So we have that the second event had only 9 possible values to choose from. And we want to choose a number that is not prime. But we've already chosen one of the numbers that's not prime. So we had 6 numbers not being prime, and we've taken one out here. So now we have 5 numbers that are not prime. And this nicely gives us a 30/90, or in other words, a 1 out of 3. But remember, that's not the final answer. We want at least 1. We don't want none. None was just a way to get at least 1. So never leave your answer here. Be very, very mindful. Okay, good. So we have 3 over 9. So the probability of at least 1, which is the 1 minus the none, which is 6 over 9, or if you want to simplify, 2 over 3. Okay, and in your exam, your quizzes, or whatever, wherever you find yourself, do well to conclude. Okay, therefore the probability of selecting at least 1 is 2 over 3, and leave your answer in the simplest possible form. Okay, good. So let's proceed. So we move on to the third problem. Probability either number is a perfect square. So the either here tells us that we are dealing with a union. Okay, good. Okay, but there's one thing about the union of without replacement that I really want you to take note of. It behaves a little bit different from the with replacements when it comes to unions. Okay, so that's what I want to say. So from what we know, the probability that either is perfect is P, that the first one is perfect, or the second one is perfect, minus both are perfect. Now this is what you have to note. When we come to the union, for the addition part, we assume we perform the experiment afresh. Okay, we assume we perform the experiment afresh. So the probability that the first one is perfect is 3 over 10. The probability that the second one is perfect is also 3 over 10. Strange, right? Yes, but that's how it works for the without replacement. When you are summing this part for these two terms, we assume each of them are done afresh. So this shouldn't be 2 over 9. It should only be 2 over 9 when it ends up that you are multiplying. Okay, take this from me. Okay, so we have PA to be 3 over 10. We start afresh with PB, also a perfect square. Now when we get to the intersection, that's where the decrease of sample space comes in. So for the PA intersection B, we have 3 over 10 times 2 over 9. Strange, right? Yes, that's how it behaves here. The sample space only reduces when the multiplication comes in. In that case, we see it as the two events are happening at the same time. Okay, yes, aside that, the remaining probabilities all have a sample of 10. You can verify from anywhere, and that is the answer that you obtain. So I'm sorry if you use 2 over 9 for the second term. It's supposed to be 3 over 10. So when you do the calculations very well, let me do that quickly here. 3 over 10 minus 6 over 90. 8 over 15. That is the correct answer. So once again, you've learned something new. Make sure you apply it out there, and that is the right way to go about with it. Okay, let's move on. Probability that this is the fourth question that we have. Probability that none is a multiple of 3. So the first one is not a multiple of 3, and the second one is also not a multiple of 3. So what is the probability that the first one is not a multiple of 3? 7/10. So because we are multiplying, we need to reduce the sample space. So the first one is not a multiple of 3, and the second one is not a multiple of 3. Okay, so instead of 7/10 times 7/10, we have 7/10 times 6/9. Why? Because one of the values not a multiple of 3 has already been taken out. Okay, good. Let's proceed to the next question. Probability first number is odd or second number is a prime, a union language going up here. So probability that first one is odd or second one is prime. Again, we have PO plus PP minus the intersection. And just as I explained in the previous slide, PA, not odd number, will give us 5/10, but it shouldn't affect the sample space for this, although it's without replacement. Because of the addition sign, we don't assume that they are done at the same time. Okay, so we also have over 10 here, and for the prime numbers, we have 4 of them. Okay, so it's when we come to the intersection. So PO is 5/10 times, then we now reduce the sample size to what? To 9. Okay, so perfect square, you still have 4 out of 9. Sorry, prime number, not a perfect square. Sorry, prime number. Okay, so when we sum this up nicely, 5/10 plus 4/10 minus we have 61 out of 90. Okay, so we have 5/10 here, and we have 4/10. The 4 is not as a result of the 5 being reduced to 4. The 4 is coming from prime numbers, and we've seen that we have 4 prime numbers. So 4 out of 10. Don't change the sample size. But when we come to the where the two of them are interacting, then we have 5/10 for the first one and 4/9 for the second one. Okay, understood? Good. So I think that's where the problems under with and without replacement ends. So I have some application questions here. Let's solve them quickly and move on to the next lecture. I already told you I have a lot of examples for you, so don't get bored. Okay, good. So let's solve this. A box contains 4 red, so 4 red, 5 blue, and 3 green. 2 balls are drawn without replacement, so when we pick a ball, we don't put it back. Find the probability that the balls are of different colors. The balls are of different colors. Now, if you attempt finding different colors, that's not bad, but it might take some time. For this particular question, the quickest way is to use complements. So now I'm asking you a question. What do you think will be the complements of different balls? If the balls are not different, then they are the same. Okay, if they are not different, then they are the same. So the quickest way to work this problem is to find the probability that they are the same. Then when you are done, you deduct it from 1 to get the probability that they are different. So the probability that they are different is 1 minus the probability that they are the same. And it's quick to work with being the same. Okay, good. So let's work it out. So probability that they are of the same color means that we can have red, red. The first one is red, the second one is red. Or, okay, or. So we can have first one is red, second one is red. Or we can have first one is blue, second one is blue. Or you can have first one is green, second one is green. The reason this approach is better is that if we say we are going with the different colors, we will have red, red. Sorry, we will have red, blue. We will also have red, green. We will have blue, green. And in this case, red, blue will be different from blue, red. Because we don't replace, they will be completely different. So you will have 6 terms. So red, blue means first one is red, second one is blue. It's different from blue, red. Blue, red is saying first one is blue, second one is red. Because of the without replacement, they cannot be the same. Okay, yes, so that gives you a whole lot of work. So you have 6 events here, but when you go the complement way, you just treat them 3, because red, red is the same as red, red, whether you turn it or so. We only say red, red. We don't have the reverse of it. That's why it's best to go with the complement way. So find the probability that they are the same, then deduct it from 1. Smartest way. Okay, so let's do that. So red, red. Okay, let's do it together. That's 1. So probability of same is equal to red, red. So we have 4 reds out of a total of 4 plus 5, 9 plus 3, 12. So first one is red. And second one is red, just as we saw. So this is an application of what we've done. The first one is red and second one is red. Or first one is blue and second one is blue. You get it from the previous examples. Or first one is green and second one is green. So this is the probability of the same. Either the first one is red and the second one is red, or, so the or comes here. The or comes here. Or the first one is blue, second one is blue. Or first one is green and second one is green. Okay, so when you compute this nicely, you end up with 29 out of 90. The probability of that they are the same is 29 out of 90. Remember, we don't want the same, we want different. So it's 1 minus, they are the same, because if they are not the same, they are different. That makes them complementary. There is no other choice. If something is not different, then it's the same. If that's not the case, don't use complement. Before you use complement, you should make sure that the thing is either this or this. So you can find this and take the probability from 1. So we take it from the probability of the same, and we get 61 out of 90. And we get 61 out of 90. So this is a very, very examinable and application question of the without replacement that we saw. Okay, good. So let's move on to the 7th question here. 3 fair coins are tossed. Let A be this event and B be this event. Determine whether events A and B are independent. A typical examination question. Determine whether A and B are independent. So for independent, what did we see? We saw that A intersection B is equal to A times B. Okay, so let's find A intersection B, and let's find the probability, and let's find probability of A and multiply it by the probability of B. If we get the same answers, they are independent. If not, they are not independent. So let's find PA intersection B first. So 3 fair coins are tossed. So the outcome for the first one is 2. Outcome for the second one is 2. Outcome for the third one is 2, because they are coins, head or tail. So first one, outcome is 2, second one 2, third one 2. So total outcomes of 8. Okay, it will be important that we list the sample space. So we have first one head, second one head, third one head, or first one head, second one head, and tail. Let's move the tail. I taught this style in a previous lecture. Then we have tail, H, H. Then we have T, T, H. Make sure whatever you write hasn't been written already. We have T, H, T. We have H, T, T. And finally T, T, T. When you are done, you count 1, 2, 3, 4, 5, 6, 7, 8. And you skim through and make sure you haven't repeated any one of them. Okay, so we have 8 of them. Now let's find the number of outcomes in A. A is saying that at least 2 heads occur. So 2 heads or 3. At least 2, so 2 or more. So this is 1. So for A, this is part of A because it has 2 or 3 heads. This is part of A, this is part, and this. So A has H, 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 T, H, T, H, and T, H, H. Okay, now let's go to B. So B is saying that the first toss is a head. So we have this H, H, H starts with an H. This also starts with an H. This starts with an H. And finally, this guy also starts with an H. Good. Now let me clean the sample space so that we can find the intersection. Okay. Okay. Now let's find A intersection B and find the probability. Okay. So A intersection B, you have H, H, H. You have H, H, T. So you are looking at the common terms. And we finally have H, T, H. So these terms are in the two of them, as you can see. Okay. So number of, so let me clear. So first, let's write the number of B. B has 4 outcomes, as you can see, and A also has 4 outcomes. Keep it down, we will use it. Let me clear this page because it's too messy. Now, for A intersection B, we had 3 outcomes. So divide by the sample space. The probability of A intersection B is 3 out of 8. Okay, because we had 3 outcomes in A intersection B. So its probability is the 3 over the sample space, which is H, which is 8. Okay, good. Now, probability of A is the number of A. A had 4 elements divided by the sample space. Probability of B had also 4 elements divided by this. Okay. So finally, to prove independence, it says that PA and B is equal to PA times PB. We had PA and B to be 3 over 8. Let's see if it's equal to 4 over 8 times 4 over 8. You take your calculator and punch 4 over 8 times 4 over 8. You end up getting 1 over 4. And we know that 1 over 4 is not equal to 3 over 8. Hence, they are not independent. Okay, so when you ask such a question, first determine A intersection B. So you list the outcomes for A, you list the outcomes for B, then you find their intersection. And you later find the probability. So the number of outcomes in A intersection B, if they are 3, then you divide it by the sample space you took it from. Then you list the outcomes in A, then find the probability to the number of outcomes in A over the sample space. You do the same for this, the number of outcomes in B over the sample space. Now you multiply these two. Okay, so the answer that you will get, you compare it with this. If they are the same, independent. If they are not independent. As simple as that. This was actually one of my favorites. Yes, you just have to do a very simple job to get the work done. So we move on to the next question, which some way looks easy, but let's enter and see if it's actually easy. So it says PA is this, PB is this, intersection is this. Yes, I said it. It's easy. I said it. So it's just a formula work. We are asked to find PA union B, which is PA plus PB minus the intersection. Okay, and we are given everything. So 0.6 plus 0.5 minus 0.35. Okay, as simple as that. We are given everything that we need, so you just fix it and you end up getting 0.75. So if you had this answer, you are correct. Okay. I think we are heading towards the last question. Okay, so there's a follow-up. Determine whether A and B are mutually exclusive. Okay, good. Okay, so we know that for mutually exclusive events, P, A, intersection B is 0. And clearly, P, A intersection B was not 0. It was 0.35. So this question is testing your understanding whether you really know what a mutually exclusive event is. We can see clearly here that it is not mutually exclusive because the intersection is not 0. Okay, the intersection is not 0. It's 0.35. Okay, good. Determine whether A and B are independent. Okay, let's do that. Determine whether A and B are independent. Okay, so we are given that PA is 0.6, PB is 0.5, and the intersection is 0.75. Okay, and we have to determine whether they are independent. So let's multiply these two values and compare it to the intersection. As simple as that. Okay, so we multiply these two values, we end up getting a 0.3. Let me confirm that anyway. 0.6 times 0.5, good, 0.3. And comparing it to 0.35, we realize they are not the same. In that case, they are not independent, or in other words, they are dependent. Okay, so they are not independent. Why? Because the product of A and B, the probabilities of A and B, is not equal to the probability of their intersection. Okay, so they are not independent. Move on. Oh, there's no way we can move on again. So that is where our set of questions end. Okay, it was a great time being your facilitator today, and I enjoyed these lessons. I hope you took several points out of our discussion. So to summarize, we saw a term called either, which means a union. We saw or, which also means a union. We saw and, which means to multiply. We saw at least, which is a complement of none. And we saw other several important terms. And one of them too that you should note is how with replacement behaves when the plus sign comes in. Treat each of them with a fresh condition, or make the sample space fresh without assuming that they are the second, so let me reduce the sample space. No, it doesn't happen when you see the plus sign. And once again, don't assume independence unless you are so sure of it. Okay, asked to find P A intersection B, don't just go ahead and multiply. See if there's any way to find the union and work with that one. If there's no way, and you are very sure of yourself that these events are independent, mostly in relation to selections. For most selections, assume independence, because what the first person will do doesn't really affect what I will do in my time. So unless you are sure, don't assume independence. Okay, it's nice having you. Hoping to see you in the next lecture. Enjoy the rest of your day.